Okay.
I don't have your email address immediately ready, but I'm just walking through Mac, seeing if you can see your Mac immediately.
Well, you know, as
Or
thought.
you can type it in, yes.
Well, just send me the email. I'll type my email address.
Yeah, yeah, Peter. Okay. Hopefully the attachment is attached. It's the attachment that you need.
Okay. Oh, it was this email. Uh, Audrey, where in the email was the Zoom link?
In the attachment.
Oh, okay. That's why we didn't find it.
Scroll down, click on that. Allow. Please, please, please. Yes, join without video.
Okay.
Easy, man. All done. I'm going to share your screen.
Okay.
There you go.
Yep. Oh. Oh no, I can't see my. Okay.
Yep.
Fine.
Yep. Okay, welcome everybody to the final day of the meeting. Hope you had a good dinner last night at Corpus Christi. I'm very pleased to welcome today Sheehan Olver from Imperial as the first talk, and Sheehan is going to speak on uniform numerical asymptotics for integral systems via Riemann-Hilbert problems. Sheehan.
All right, thanks, and I'd like to thank the organizers for inviting me to talk and give the first talk the morning after the conference dinner, which is the second Newton Institute program in a row that I've been asked to do that. So I guess the word is getting around how good of a first speaker I am after dinner. So this talk is really about stuff that I did roughly 10 years ago, but I think many people in the audience might not be familiar with it. So I wanted to sort of introduce Riemann-Hilbert problems, and being the first talk, I'll do it at a very basic level, well, hopefully very basic. So hopefully this will be appreciated to a broad audience. And essentially the point of this talk is that, so for integrable systems like Painlevé, KDV, NOS, we have Riemann-Hilbert problems. These have been used successfully to prove rigorous asymptotics, but they can also be used to do numerics, to compute solutions. And in many ways, the numerics is a lot easier than the asymptotic analysis. That some of the difficulties, for example, we've seen in previous talks by Alfredo and others, this problem of finding parametrices can be avoided by doing numerics. So this is the point of the talk, and there are some interesting sort of outcomes where numerics can work, where the asymptotic analysis, well, it might be possible, but hasn't yet been done. Okay, so here are 3 examples. Actually, I'll only do the second 2 in this talk, so let's focus on the second 2 examples. KdV is a classic shallow water, classic fluids equation related to shallow water that happens to be integrable. And then Panlevey 2, which we've seen a lot in this program, is a second order nonlinear ODE. And both of them happen to be integrable and happen to have Riemann-Hilbert problems. And the point of this talk is, rather than solving them as PDEs or ODEs, we can numerically compute them by using the Riemann-Hilbert problem. And the thing I really want to emphasize is a Riemann-Hilbert problem is like an integral representation. So for example, area equation, we all know, okay, you should never say we all know, because someone might not. Does anyone here not know the area equation? Okay. Probably in this audience, everyone knows the area equation. But so the area equation is this, but it also has an integral representation. And I'm going to write it because I'm going to come back to it. And I'm going to write it in a slightly non-standard form, but one that will sort of look like the Riemann-Hilbert problem that will come up. So this is the ODE with certain initial conditions, let's say, but we can instead think of it as an integral. I'll write this for now. I might be off by a factor of 2. So if anyone, I am. I'll just write this. And I'll integrate with respect to Z, which might be a bit weird, but it is what it is. So either we can think of this as an ODE and numerically think of solving an ODE, or we can think of it as an integral. This is maybe not, this is actually one that is not in the DLMF, but it's trivially equivalent to the ones that are in the DLMF. And rather than compute this ODE, we can compute this integral. And it's the exact same with Panlevey 2. So if you ignore the nonlinear part, it's exactly the area equation. We can either think of this as a nonlinear ODE, or we don't have an integral representation, but we do have a Riemann-Hilbert problem. So that's sort of the point of this talk. So don't think of it as an ODE. Think of it as, well, in this case, an integral representation. In that case, a Riemann-Hilbert problem. Okay. So then the question is, why not just use standard numerical methods, which is what would be the obvious solution. So let's say we wanted to solve KdV. And the standard approach is you replace, so KdV on the real line. And a very basic approach is you replace the real line with a periodic box, use Fourier, and then evolve in time. And this reduces a PD essentially to ODEs. And if you plug in well-known solutions like solitons, this works perfectly well. So solitons have nice behavior. This is computed on the real line, but had you done it in a periodic box, it would have worked equally well because it has exponential decay, and it never sees the boundary that you've imposed. But if you do a general solution, so solitons are not the typical solutions. They're very special. If you perturb slightly away from a soliton, this is the more general behavior. So you can see we have solitons moving to the right, but we also have this dispersive tail moving to the left. And it moves incredibly quickly. So this is at t equals 20. 20 is not that big. I don't think it's that big. Well, for the solitons, they've not moved that much. On the other hand, the dispersive tail, which is here on the order of 10 to the minus 6, has moved to minus 13,000. Now, a minus 13,000 box periodic box is a pretty big box. You need a lot of Fourier modes to compute the solution. I don't even know if you could compute this with classical numerical methods at t equals 20. Whereas, obviously, we did compute it. We have some way, and the way we did this was Riemann-Hilbert problems, because if you think back to this ODE versus integral representation, an ODE you would think of as evolving starting from an initial condition. The integral representation, we can just plug in whatever x we want. And here, we have a Riemann-Hilbert problem. We can plug in whatever x and t we want and just get out the solution. So actually, we computed the solution in that box, in that window, and in this close to the origin, but we didn't actually compute the solution for all x and t in between. Okay. Going beyond that, there's even more interesting examples. This is by my collaborator, Tom Trogdon, of solutions that don't decay. So this is an example of something that is quasi-periodic, so related to sort of finite genus solutions to KdV, plus a perturbation. And he was able to solve this solution, which would basically be impossible to solve at all because it's not periodic. We can't truncate the boundary because this solution goes off to infinity because he had a Riemann-Hilbert problem. Okay. So this is the answer, and the short of it is if you look at the complexity, Riemann-Hilbert problems can have much better complexity than standard numerical methods. So this is the rest of the talk. I'm not actually going to talk that much about the actual numerical method because I don't think for this audience it would be the right thing to talk about. Instead, I want to sort of try to connect asymptotics to Riemann-Hilbert problems and hopefully explain how these things relate. And numerics gives us a tool that we don't need to do the full asymptotic analysis. It simplifies the explanation. So I'll start with a brief explanation of the Riemann-Hilbert problems for these two equations, panel of A2 and KdV. And just like an integral representation, which you can deform in the complex plane, a Riemann-Hilbert problem you can deform very similar to the integral representation. So I'll talk about what's called nonlinear steepest descent or Dijk's steepest descent, where you take a Riemann-Hilbert problem, which is very much like an integral representation, and deform it through stationary points, very similar to classical asymptotic analysis. But there are hiccups that it doesn't. There are cases where it doesn't proceed exactly like integrals, and that's where things get really interesting. So I'll talk about what's called the nonlinear Stokes phenomenon, where the classic techniques of deformation through passive steepest descent break down in certain regimes, and then you need to introduce other tools. And the last part is looking at examples where, so all of this is sort of classic Riemann-Hilbert analysis. The last example is showing that because we have numerics, we can go beyond that and do uniform approximations to these equations that are asymptotically accurate. So here we can either think of this as a tool to get asymptotics out, or we can think of it as a tool to get numerics out. And people, what's her name? Teme and Gill, there's a whole camp of people who look at computing special functions like this. Okay. So what exactly is a Riemann-Hilbert problem? So essentially, we want to think of an analytic function with branch cuts. So phi of z is something that's analytic off some sequence of contours, not necessarily just a straight line, but with, say, things like that. And so we could think of it as like a piecewise analytic function, or these could actually be finite truncated intervals. And we want to find an analytic function that's analytic off these contours that has nicely defined left and right limits And what we're given is the jump. So like, the question is, given an analytic function, can we recover it from information about its branch cut? And it turns out you can. And numerically, what we do is we take this Riemann-Hilbert problem. So we're given G. G is a function on these contours, on these branch cuts, that tells us a relationship between the limit from the left and the limit from the right. Numerically, we plug in, we write it as a Cauchy transform of a function defined on the contour. So this sort of generates a function analytic off the contour for a new unknown v. So now the question is, don't find phi, find v. V is a univariate, is sort of a one-dimensional function on these contours. When we plug that in, we have changed the Riemann-Hilbert problem to a singular integral equation involving, we could write it in terms of Hilbert transforms, but here I've written it in terms of left and right limits of the Cauchy transform. Okay, this is a nice linear equation. It's linear in V. So you can plug in a basis, do whatever numerical method you want. And in my case, I developed a spectral method. So I used piecewise Chebyshev polynomials. So I chopped this up into pieces. Each piece was represented by a mapped Chebyshev expansion. What are the coefficients? Well, you just make this equation true pointwise at a sequence of points. Okay, so I'm not going to say that much else about the numerics. The main point is, if this jump, if this function g is nice, whatever nice means, you can effectively compute the numerical solution to a Riemann-Hilbert problem. Okay. And so essentially the name of the, and it's the same with integrals. If this integral is nice, we can use quadrature, trapezium rule, or Gauss quadrature, or whatever we want. If the integrand is not nice, well, that's not going to work. So as I've written it here, this is not nice. But if x is small, we can integrate, and this is sort of leading to the later part, over a different contour, like this, which it goes through the path of steepest descent, and this makes the integrand nice. So when the integrand is nice, we can integrate effectively using numerics, and it's the exact same with Riemann-Hilbert problems. If this g function is nice, we can effectively numerically compute Riemann-Hilbert problems. So from a numerical perspective, that's sort of the name of the game, is you're given, say, something like this. Just instead of an integral, it's a Riemann-Hilbert problem, and we want to deform it so it's nice. So let's start with the Riemann-Hilbert problem for panel of A2. And you can almost see the area equation hidden in here, the integral representation. So if we ignore that and that and that and that, here is effect is actually equivalent to what I wrote. So if we only had this contour here, and we asked what, so essentially we would ask for an analytic function that's analytic in this sector and that sector with these jumps, and then took the limit as z goes to infinity. Well, it turns out, and it's sort of like a one-line calculation, but I won't put it, that would be exactly equivalent to this integral representation. So essentially, the Riemann-Hilbert problem has this very airy-like flavor, but instead of just being an integral along this, it's almost like 6 or 3 coupled airy functions together. Now, the ODE is nonlinear, but the Riemann-Hilbert problem is linear. We can replace it by a singular integral equation, a linear singular integral equation. And that's really the power here, is that we've replaced a nonlinear problem with a linear problem. And if we can solve this, we can get out the value of a solution, well, any solution to panel of A2. So here we're going to treat panel of A2 as a special function with 3 parameters. Now it's second order ODE. There should only be two. They satisfy this relationship. These are called Stokes constants because they are Stokes constants. So essentially there's a Lax pair, there's a linear ODE, and if you do Stokes analysis on this linear ODE, these are the Stokes constants related to that. But I won't go into those details. But essentially, rather than thinking of giving initial conditions to this, we think of it as we're giving these Stokes constants. And these are parameters in the Riemann-Hilbert problem. Everything else looks exactly like the area integral representation. Okay. Now, if x is small, this is actually, so let's say x is 0. These are actually already on the path of steepest descent. So we have a nice, jumps. We can plug it into the toolbox. We can represent on each of these contours, we can say truncate it and represent it by the solution to the singular integral equation by Chebyshev expansions. And we can just plug this into the numerical toolbox and get values out. So here's a classic example of that, the Hastings-McLeod solution. As an ODE, we think of it as given initial conditions either at infinity or minus infinity. As a special function, we think of it as given these Stokes constants, I 0 minus I, but this is what it looks like. And it looks pretty nice. There are definitely other numerical ways you could compute this, but we can also use this Riemann-Hilbert problem because x here is small. The jumps are not too oscillatory. The jumps look like this, and think of the integral representation on this contour. If x is reasonably small, that contour is going to be okay. But this example also shows some of the interesting aspects of these nonlinear equations, is that this looks like a very nice solution, but if we perturb it even slightly, either as an initial condition or as Stokes constants, we get completely different behavior. I'm not sure I got the colors right here. If Alexander wants to correct my colors, now's the time. But because one I'm perturbing below and one I'm perturbing above. But yeah. Okay, this one is probably correct. Or if we perturb a different way, so this is say perturbing the initial conditions from the right or perturbing the Stokes constants, we get this behavior. One is sort of oscillatory. We'll actually come back to this. One has poles. So this Hastings-McLeod solution is right at the cusp of a transition from oscillatory to poles. If we perturb the other way, so think of it as perturbing the initial conditions or perturbing the middle Stokes constant. This one might be wrong, but I might have got the colors wrong, but then we get poles there. Okay. But because we have this Riemann-Hilbert problem, we can just plug these in. This is actually very challenging from an ODE perspective. So if I give you this ODE and say, what's this red curve here, and you did it naively, you would run into the poles, and well, there's what's her name? Weidemann and Fornberg have a clever scheme to avoid this, but if you didn't use a clever scheme, you would sort of be out of luck. But because we have a Riemann-Hilbert problem, we can just plug it in and get out the values. More generally, here are some other solutions plotted in the complex plane for small x. And because we have a nice jump, we can just plug it in and get these plots. Okay. And this is sort of the generic behavior, is this sort of pole fields, which we've seen in many other talks. So that's an ODE example. Potentially more interesting is the PDE examples, so KDV. And just as in the ODE example, we sort of tied things to the classical linear ODEs. For PDEs, we're going to tie things to the classical linear PDEs. So if we wanted to do KDV, which is a nonlinear equation, we'll sort of think of it in terms of linear KDV. Now, this is a linear PDE. You can just plug in Fourier-based. You can do the naive thing and or the standard thing and do a Fourier transform. Taking a Fourier transform makes time evolution trivial. So the time evolution of the Fourier transform is trivial. And then we can recover the solution to this linear PDE at any point t and x by just computing the integral. For nonlinear KdV, we have something very similar. We have some sort of transform that's like a Fourier transform, which makes time evolution trivial. And then the inverse part will be the Riemann-Hilbert problem. Okay. So how do we do the direct transform? Well, this is related to eigenvalue analysis of the Schrodinger equation. I'll just briefly do some examples. So this is a linear ODE. We can use conventional numerics. I won't go into details, but say spectral methods, and compute the discretize the linear Schrodinger equation, compute the eigenvalues of the discretization, and that gives an effective way of, say, computing these discrete. So essentially, we have something like a Fourier transform. We also have discrete points. The discrete points are the eigenvalues of the Schrodinger equation, and we can use sort of standard spectral methods to compute these very accurately, so up to the order 10 to the minus 13. For the other part, the reflection coefficient, well, this is related to scattering. So we have sort of a wave coming in from the left, and we want to see how it's scattered by a potential. We can also use spectral methods where we chop off the real line into two halves, compute these linear ODEs on the left and right, relate the solutions to the linear on the left to the linear on the right, the numerical solutions, and that tells us this reflection coefficient. So this is sort of standard ODEs. And so that's how we would do sort of the direct transform. And here are two initial conditions and two reflection coefficients. Think of these as Fourier transforms. One key point here is, and this will come back to sort of bite us, is that generically, if we put in initial conditions, the reflection coefficients are always equal to -1 at the origin. Okay. So that's the analog of a Fourier transform is spectral analysis. The analog of an inverse Fourier transform is a Riemann-Hilbert problem. That was supposed to appear. Anyway, so here is the jump on a contour. We also have jumps related to the discrete eigenvalues. These are in the complex plane. Provided x and t are small, these jumps are nice, and therefore we can effectively compute KdV by solving the Riemann-Hilbert problem. So you do the spectral analysis of the initial condition as a potential, evolve for small time, and plug this in. And if t and x are small, this is not too oscillatory because the reflection coefficient decays exponentially. You know that the reflection coefficient R is -1 at the origin, which means this actually vanishes at the origin, which is a key point. Okay. So that's the sort of what you would do with a Riemann-Hilbert problem in this like non-asymptotic regime. Now, if we took area equation and let x become large, we wouldn't want to use this this integration contour. So we wouldn't want it to go through 0. We would integrate through, well, we would figure out the stationary points, which I think in this case is I/2. Are there any experts in asymptotic analysis in the room? Is it I/2 or? What? It will depend on x. Oh, okay. Okay, so then you do the change of variables. That's a good point. Where's my notepad? Okay. That's a really good point. So I think we do think I have it in the next slide. I'm not going to, forgot to write it down here. It's right here. So if we do just a simple change of variables, z goes to square root absolute value x. Well, x here is going to just be positive. You can use this for complex x, but in this case, we'll just think of x as positive. Then we get this. This is our oscillator. Then its passes, its stationary points, I think, are I/2, and we can deform this contour through this path. Okay. Now numerically, we don't. So asymptotically, we can use this to get out asymptotics. Numerically, we can just sort of truncate it. We can say cut this off and numerically integrate this contour. And actually, it doesn't even matter that we are on the path of steepest descent. If we make the contour small enough, we can just say it's a straight line. So this is what we would do with an integral. And in certain settings, we can do the same thing with the Riemann-Hilbert problem. Okay. So we can do a simple change of variables, just like we did there. And this gives us a Riemann-Hilbert problem that looks like what our integram would look like. So now we have the x is just a constant in front of this fixed oscillator theta. Very important here is that I've set this Stokes constant to 0, which has sort of removed, originally I had 6 rays. I've gotten rid of it. In this special case, we can do exactly the same thing. But it's sort of important to note here is that in the integral representation, we only have e to the I theta. Here we actually have e to the I theta and e to the minus I theta. So when we do the deformation, we actually get 2 contours, one through I/2 and one through minus I/2. But in this simple case, we can just deform through these paths of steepest descent. Our jump, which would have been oscillatory when x was large, has become non-oscillatory. We can plug it into the numerical framework. And just as you would do numerically for an integral, chop it off, and then you make sure that the scales with x so that we don't see the sort of, so that the function becomes nice as x becomes large. We can chop off these Riemann-Hilbert contours, scale them, plug it into, that means that the jump is uniformly nice, and we can get numerics that are uniformly accurate as x goes to infinity. Okay. So this is what I mean by numeric asymptotics, is it's a numerical method, but it's accurate in the asymptotic regime. Okay. And here's an example. So if I set S, which is the first Stokes constant, to I guess this is the Hastings-McLeod solution. It actually looks a lot like the area equation. I'm using this numerical method in this regime deformed. It looks a lot like the area equation. But we can also do sort of other examples, say, let S become large, and we get this interesting sort of behavior. Okay. Classically, the Riemann-Hilbert problem would just give you the asymptotics. Here, because we're doing numerics as well, this is accurate in this whole sector, and therefore we can accurately compute these poles. I don't know if there's any asymptotics when the Stokes constants become large. Are there? Is there any asymptotic analysis when the Stokes constants become large? As x goes to infinity.
You mean some sort of the double scaling?
Yeah.
No, okay, that's good. There are some but few results.
Yeah. But that's the nice thing about numerics is this is an example where I'm sure the experts could do the asymptotic analysis, but here the numerics, you don't need to be an expert. You can be me and get out the values. Okay. So that's positive x. So this is x greater than 0. X less than 0, you sort of, now the stationary points are at a half and minus a half. And I think if you deform that contour, you would sort of, along the path of steepest descent, you would get this, and then come back from infinity. Okay. And in general, so before, in special cases, it was the same as linear deformations. Here, in general, it's the same as linear deformations. We can take our jumps, deform them through, so this is exactly the, well, we haven't gotten the other part yet, but this is deformed through the stationary points. We can just deform it as you would an integral representation. There is a catch here, is that we have this annoying contour here connecting the two stationary points. That's not good because the solution will be oscillatory on that contour. So we need to sort of get rid of that so things are localized near the stationary points. So if we look at this contour, it has exactly this form. This is the jump. If we can do a matrix decomposition of this, think like an LU factorization, we can then split a single contour above and below. So here the issue is we have two oscillatory modes. So if you deform along one path of steepest ascent, that's the other's path of steepest ascent. So we need to somehow split these two oscillatory modes. Fortunately, we have this, if you just do an LDU decomposition, we can do this. We can decouple the two modes. Okay. But you can see here exactly why this is a special case, is because this would break down in that setting. Okay. But anyway, so it's slightly more complicated than an integral representation, but in spirit it's the same thing. You find the path of steepest descent. Here you see exactly this contour that we had in the linear case, plus these other contours, because we have both plus and minus. And having done this, okay, we still have this diagonal thing, but we can sort of prune out a single diagonal jump because we can just write down exactly something that satisfies that jump. And doing that, we get something that's localized through the stationary point. So just on the numerical level, for the area equation, we would take this, write an interval that's passed through the stationary points. Now we get something, and then we would scale those intervals as x went to minus infinity. Here we get something very similar, but instead of just an interval, it's this sort of contours. We just scale it down as x becomes very negative. And these jumps will, it might not be obvious, but they will behave very similar to the jumps here, or to the integrand here, and will be nice as x becomes very large, negative large, and we can do effective numerics. Okay, and this is a very clear plot of I'll skip over that, but it's not just one plot. It's many very clear plots. But okay, this one is sort of clear. So this is an example of some solution with arbitrary Stokes constants, and they happen to have poles, but we can effectively do numerics that are asymptotically accurate, and x can be as large as we want it. Okay. We can do the same thing with KdV. So just like area equation, if you can deform area, the integrand for area, you probably know how to deform the integrand for linear KdV, because it looks very similar. If you know how to deform Pan-Loureiro, you probably know how to deform this, because they both have Z cubed plus something. Okay. So we can, in many regimes, use these same deformations as Pan-Loureiro, which are really motivated from the area equation. And effectively compute solutions to KdV. So here, we have a bunch of regions. I'm not. I'll come back to this. These are the interesting ones. The dispersive region is exactly this. So this is sort of the dispersive region for deformation for KDB. So it's going to be very similar to that because the integrand is the same. So you do the same thing. Well, it's not an integrand, it's a jump, but you do the same thing. And this would be this sort of soliton. So here we would deform the Riemann-Hilbert problem for KDB through the stationary points. It's not constant now. We have this reflection coefficient, this thing like a Fourier transform. But effectively, in these regions, dispersive soliton, it's very similar. The middle region, Pan-Levé, is sort of the undeformed case. But then we have these interesting things in between. Okay. So here's the soliton region. Looks a lot like this deformation. We have these extra poles. They're actually the main thing. The contours sort of disappear because they exponentially decay, so all you get is the solitons, which correspond to these poles. But other than that, it's very much like deformation of an Airy equation. Pan-Levé region is like the undeformed case. Like if we use this original contour, if x and t are, if x is small, you actually don't need to deform because the standard thing is basically on the path of steepest descent. And we get this sort of deformation. And then the dispersive region looks like the negative x case. Okay. So when things are simple, things sort of proceed very much like linear steepest descent. But what happens when things are not simple? So if you remember, at the start of the talk, I showed the special solutions, the Hastings-McLeod solution. But if we perturb slightly away from it, we got very different behavior. These techniques, these sort of linear deformations, sort of break down in that regime. So what can we do? So essentially, let me see if I can go back. What actually is a problem? So the problem here is well, now I have lots of problems. Okay. I also lost my. The problem here is the way we managed to deform this through the passive steepest descent. Here we had two coupled oscillations. Their passive steepest descent are sort of opposite of each other, conjugate. When this is 1, and the way we did it was an LU decomposition. Well, anyone who knows Gaussian elimination knows that if you have a 0 in the first entry, you can't do LU decomposition. So essentially, our decomposition is broken down because we have a 0 there. So here, I did the LU decomposition of that, and we see if that is 1, we get sort of a pole. And our Riemann-Hilbert problem becomes ill-posed. Oh, I guess I'm running out of time. Well, fortunately, there's a trick where you introduce a function. We change our oscillator to something that has the same asymptotic behavior but has a branch cut. And so you essentially introduce something with a branch cut, and that can fix the problem. So I won't go into the details, but essentially this is our picture. These are different Riemann-Hilbert problems. These are this is similar to the linear case. But in these cases, we need something different where we've sort of introduced the so-called G function. Okay. So now the interesting question is, what happens with this transition? Which is, again, I think, an example of something that's missing in the asymptotic analysis.
This one to split off. So this is
Okay. Okay. So 10 years ago when I made the slide, 10 years ago when I made the slide. Okay. Yeah. Anyways, I've sort of run out of time, but so we have to introduce something with branch cuts, but now we have 2 branch cuts. And when I did this slide, the asymptotics wasn't there, but we could do the numerics. And I'll just sort of jump to the, yeah. Yeah. And then probably he did the next step and figured out the parametrices. But because I don't need to do that, I can get results without doing that. Okay. Yeah, and so then we get these. Now the interesting thing here is that the Stokes constants, to get sort of the stable asymptotics, you need the Stokes constants to depend on x. Okay. And then we get sort of this. This is how we transition from one to the other. Okay. And you can do the same thing with KDV. Again, there's, I won't go into the details. I'll do the movie, if the movie works. Oh, the movie doesn't work. Okay. So that's, I'll end there. I will leave a question. So there's something interesting here with having Stokes constants vary with x. So let's say we did, so here in the linear case, we know linear KDV looks a lot like ARI. And we can actually get a uniform approximation to a solution of the linear KDV in terms of the ARI equation. So rather than redoing all these deformations, so the deformations are exactly the same for KDV as ARI, we could instead use the ARI function as sort of a uniform approximation. So, and we have the same question in this KDV case, is that if we could use Panleve 2 to get, the deformations are exactly the same for Panleve 2 as KDV. So here was like ARI, linear KDV, it's the same Panleve 2 KDV. Rather than doing these deformations, repeating the same deformations of different regimes, can we actually use Panleve 2 but with varying Stokes constants to get a uniform approximation? And I think for the general audience, this relates to an interesting question because, I mean, the exponential asymptotics experts in the room probably use error functions or other special functions to capture the uniform behavior. Potentially in the nonlinear setting, Panleve could serve a similar role by having this, but allowing these Stokes constants to vary with x. So I'll leave that as a question for the audience. Can you actually use this to do better uniform asymptotics for nonlinear problems? But anyways, I'll stop there.
Any questions? Ah, Nalini. Yeah, that's on.
Thanks very much. Sheehan, for a very interesting talk. I wondered what you meant by Stokes constants varying with x. X is the independent variable, right, of the Panleve equation. So where does the iso part of the isomonodromy come in?
Well, yeah, so that's the interesting thing is now we're not treating it as like an ODE. We're treating it as just a special function.
I see.
So, which is possibly why it's not sort of obvious how. So in the linear case, it's when you have linear things, the Stokes constants are linear. And so the relationship, so if you wrote down a uniform approximation to say KDV, you would just get like the Fourier transform evaluated at the stationary point times some area thing. Here it's a nonlinear relationship.
But then it's no longer Panlevey 2, is it?
Right. But it's a special function that somehow has, this special function has captured these different deformations. The movie would have been great, but it didn't work. But so we have these different deformations that look a lot like essentially the same as the deformations for Panlevey 2. And yeah, so that would be the idea. But yeah.
Okay. One more thing was when you talked about the Stokes constants going to infinity, on the cubic surface, which is the monodromy manifold, there are lines at infinity. You can think about it as written in projective coordinates, compactified in projective space. You have lines at infinity, and those are objects that correspond to certain asymptotic behaviors. So I think there is a geometric interpretation of what you might have been seeking as well.
Okay.
Any other questions? Yeah.
Hi, just a very small question. Using your analogy with either an integral representation or a differential equation, in those cases, usually in advance, you can sort of decide where the turning points will be, the Stokes lines, so you have an idea of what behavior you could expect in the, say, the whole complex plane. But for this problem here that you have so much variety and such different types of behaviors, can you, like, a priori, if you don't know the equation, decide how many sectors you're going to have to consider, what type of behavior you're going to expect?
Well, a priori to what?
Like if you know already Panlevey 2, then of course you know that you can expect this here, this there. But if somebody will throw a nonlinear equation at you that you haven't seen before,
I mean, that's most of the Riemann-Hilbert business is answering that question for each different example that comes up. Because it's not trivial. Would you agree? A priori, can you do these deformations a priori, or do you have to think about it? And I think you have to.
If you don't know the equation already, right? If somebody gives you a nonlinear equation that comes from somewhere, could the Riemann-Hilbert analysis decide in advance which type of regions you're going to expect and what behavior in those regions?
This is partially what actually was a question what Alfredo yesterday also he addressed it too. So this is, I would say, this is a sort of, okay, according to my experience, this is a combination of just some experience, skill, and indeed some hints. So you have, for instance, historically, before steepest descent method was introduced by Dave and Joe, we used, and we already, did asymptotic analysis using the asymptotic solution of the direct monodromy problem. We kind of do sort of WKB analysis, which is probably now it is close to, at that time also IKEA did the same, similar things. And when you do this way, the situation more determined. You just, first of all, you look at the equation and you see what sort of behavior is possible for solution. It is more or less easy. Well, what Nelly Niven said about that, you can easily see, say, elliptic asymptotics. You can see this truncated asymptotics from the equation. And then you do what? You take this ansatz, plug into the Lax pair, and try to calculate asymptotically the monodromy data. And this is, well, it is challenging, but this is a kind of the regular way. So there are problems with the rigorous justification in this approach, and many other kind of the downsides of this method. But this part is indeed, so in particular, these G functions, which sometimes indeed very strange, why you choose such as G functions, in this approach, they just come as a, as a usual WKB ingredient. It is a linearization of your matrix A. So this is a kind of eigenvalue of your matrix A. So, so this is partially, I think, answers to you. So when you have all these things, you then start doing, and plus, of course, some kind of experience and skill. So it is just like in any asymptotic analysis. And I remember there was a very good paper, long paper of one of my great teacher back in Russia. It is Babbage, Vasily Mikhailovich Babbage. He wrote many years ago the paper which was called The Art of Asymptotics.
I will just mention Folkmar-Bornemann has an algorithm that automatically figures out these deformations by looping over. So you need to come up with a matrix composition. It's an LU or UL. It loops through all possible ones and then deforms. But that doesn't tell you much about the asymptotics.
No? Okay. Any other questions? No? Okay, well, thank our speaker. Thank you very much, Sheehan.
Maybe here, so a little higher. Is it working now? But is this low sound?
Yeah, it's not really for in the room. It's really for online.
Okay. Thank you very much.
Okay. Okay, so now we're very pleased to welcome Dan Dai, who's from City University, Hong Kong, and he's going to speak on asymptotics of Fredholm determinants associated with high-dimensional kernels.
Okay, yeah. Thank you very much. And first, I would like to thank the organizers and for organizing such kind of very interesting activity, and moreover, just give me the opportunity to be here and present our recent research. So this is joint work with Sheehan and Renzang. And this is a brief outline of my talk. First, I'm going to show you what is about this higher dimensional kernel, and in more precise, we are going to study the PLC kernel and the hard edge PLC kernel. And once we have the kernel, we want to study the corresponding Fredholm determinant or the gap probability. And for the Fredholm determinant, we mainly want to know two things. The first one is about the integral formula, and the second one is about its asymptotics. And for the integral formula, we're going to see that there's some kind of like the less pair hiding behind the integral system structure and also the Hamiltonian. And for the asymptotics part, we're going to use the Diffie-Hellman steep descent method. Okay, and so where should we start? And we know that the Fredholm determinants are related to many things, and today we want to start our journey with the determinantal point process. Okay, then first we have a configuration of the points, and we require that they are locally finite in the sense that for any bounded interval AB, the number of the particles inside are finite. And then we say here, and then here this point process is just a probability measure over all such kind of locally finite configurations. And we say a point process is determinantal if this k-point correlation function can be given in such kind of form. And k is called the correlation kernel. Okay, so once we have this kernel, basically we know all the information about the point process. And we also, and for this determinantal point process, that causes related to many different models, like the random unitary matrices, Dyson-Brown emotion, and the free fermionic theory, and also the quantum gravity. So maybe we just start from this Dyson-Brown emotion, so I can show you some nice figures. Okay. So indeed here we're considering this one-dimensional Brown emotion. So this is like the t-axis. This is the x-axis, and we have certain particles. We require that it starts from a point 0 after time t equal to 1. It returns to, say, the point origin. And we have some others, and we require them to be long intersection during this time interval from 0 to 1. So this is the path we have, and then at an arbitrary fixed time t, say t here, and we consider the position of the particles, and then the position will form a determinate point process. We also know that this is for this model, it is closely related to the Gaussian unitary ensemble, and the underlying special function will be the Hermite polynomial we are very familiar with. And so this is like the simple case. And we can also change this model a little bit such that it starts from the point origin, but now we require like half of the particles goes to the point 1, and the other half goes to the point -1. And so you can see for this case here at the very beginning, all the particles are staying in the 1 interval. And here, right, this is t-axis, so here is in the 1 interval, and later on, you will go to split into 2 of them. So here we have a critical time, and the critical time here, and now this, the interval will split. So here we have like a 1-cut to a 2-cut transition. And for this case, the corresponding matrix model will be the Gaussian unitary ensemble with external sources. And we also have the underlying special function. Now will be the multiple Hermite polynomials. Okay, so this is the case. And we can also have the other one with this so-called square Bessel passes. It is very related to the Brown emotion. Indeed, if you have a d-dimensional Brown emotion, we study the square of the distances to a point origin, it corresponding to the square path with this parameter alpha. We know this alpha inside the Bessel function. Alpha is equal to d over 2 minus 1. And because we have this kind of structure that with the distance, you can see the path can never cross the point x equal to 0. So here we have a wall, and for the upper boundary, it's similar to the previous case, but now here we have wall, and for this case, we will see that we have the hard edge. And for this case, we also have the special function behind that. It is again the multiple orthogonal polynomial, but with modified Bessel weight. And this is our some kind of figures, and now usually we are interested in the case where the number of the particles becomes large. Of course, and for different n, the models are very different. We have different special functions. We have different formulas. But the good thing is that when n goes to infinity, we only have 3. In general, we only have some simple classical limits. And these are like we have three classical limiting kernels. And the first of course, we need to choose this spatial point. We need to consider a reference point to consider. If we consider here close to here we have a boundary. If we consider here close to a boundary, we have this one. Now we will go to the so-called the soft edge. In the soft edge, we will have the so-called the area kernel. If we stay inside here, we will get the sign kernel, and this is for this like the GUE case. And of course, by the way, for in different limits, and first of all, the order of this n is different, and moreover, this number c is different in different cases. And when we can get this hard edge business, this one comes from in this model here. If we stay in this part, and now we get, because the particles just they have to go to the point origin, but they have not crossed the wall, so they have to squeeze together, and then we get this here we will get the Bessel kernel. But we also realize that there are two special points. The first one is in this first model here, we see that near this critical point, we have this 1-cut to a 2-cut transition. Is like here in the middle here, we have the sign kernel, but somehow we will split into 2 area kernels. So we can expect that something different will happen. And in this case, it's also similar. We have on the left, we have on this green part here, we still get the area kernel, but now we will go to the Bessel kernel. So in both cases, we have this kind of critical situation, and now we want to study their behavior. And then we have the so-called after the double scaling limit, we have the kernels we want to study today, which the first one is this POC kernel is obtained by Brecher and Koyalas, and in this paper, and here is his first of all, we just because we take this ports to be symmetry, so now this cast splitting will always happen near the origin, and so this is not very important. The important thing is about this typical time, and we near the critical time, after this kind of scaling, we will get the PLC kernel. I'm going to show you the formula for the PLC kernel later, and the PLC kernel can occur in such kind of Brown emotion paths. It also occur in some other matrix models as well as the random partitions. And for the square Bessel paths, and we have the similar thing, and again near the point origin and near this critical time after double scaling limit, we will get this so-called hard edge PLC kernel, and now we have this additional parameter alpha, which comes from the Bessel function. Okay, again, but you see this order here are different, right? The order here are different. And for the hard edge PLC kernel, it also occurs in some in various different models. And then we can take a look at the formulas. And this is the formula for the PLC kernel. It was a little bit more complicated than the classical ones. But I think the main point I want to tell you is that, first of all, now the functions P and Q here will be given in terms, will satisfy this third order differential equation. The first one is actually the PLC differential equation we have seen in George Silton's talk on Tuesday, but without the parameter epsilon. And the other one is a little bit different. The second one is that now we have more terms in the numerators, and then for this case, later on we're going to see that maybe we will have like in the product with a higher dimensional vectors. Okay, so this is for the PLC case. And for the hard edge PLC case, we will have one additional parameter alpha, so the formula becomes a little bit more complicated, but we have a similar structure, I guess, and we still have the third order differential equation, and we have some similar terms here involving both P and P prime and P double prime. Okay, so these are our kernels, and this kernel is obtained in the paper by Koilas, Martinez, Finkelstein, and Frank Wolowski about more than 10 years ago. So once we have kernels, and now what we are going to do, as we have mentioned that, because we start from the determinant point process, so all the information is contained in the kernel. So once we have a kernel, we can do some things. And typically, and in this in the study of the point process or the random matrix theory, a very important quality is to consider so-called the gap probability, or this probability that there's a low particle in certain interval J is given. And for our case, and we are very lucky because finally we can rewrite this gap probability in terms of the Fredholm determinant. And here this one is Kj is trace class operator. It's an integral operator acting on this L2. J is the gap you want to study, and with our integral with our kernel K. So this is the formula for the general case, and this is, and again we can take the area kernel as an example, which is actually a very famous example. We take the kernel here to be the area kernel, and now because area kernel gives us a boundary, if we consider the upper boundary, we can take the interval here to be, say, from S to infinity, we get a formula like that. Okay, so this is our Fredholm determinants. This is like our starting point. But now, of course, we have infinite series, so it's not easy for us to study the properties. And so, and a great result is given by Trace and Vedem, and they showed that this kind of infinite series actually can be given in terms of a closed form, which is very convenient for us to study. And this is the celebrated Tracy-Vedem distribution, and this Q function here is actually the one we have seen in Sheehan's talk. It's a Hastings-Malloy solution for the homogeneous parameter 2, which is very nice. It's, for here, we choose the coefficient to be 1. In Sheehan's talk, it's -1, but it's just very similar. Okay, so this is the formula. So now you see that we have a closed form, so everything is clear, and nowadays I think we know more information about the Hastings-Malloy solution, so we can study this property this distribution very well. And sometimes we also want to rewrite the formula into a slightly different form, and by using integration by parts, we can get this Hamiltonian, right? This HP here is actually the Hamiltonian of the parameter 2, and here this Q is just the Q will satisfy our inhomogeneous parameter 2 equation here. And for our case, we think that this Hamiltonian is will be more convenient. We are going to show you why we like this Hamiltonian expression. And so this is one thing we know this integral formula for the area kernel determinant. Now we have the Tracy rhythm distributions. Otherwise, to study the asymptotics. Okay, so how is the case when S is changing? When S goes to plus infinity, of course, it's trivial. We just get 1. When S goes to minus infinity, now it's a very different story. We have this Q function is tested by loss solution, and now we need some efforts. And indeed, in this paper by Tracy and Widom, and they have derived this asymptotics. Even they conjectured the constants. And by the way, the constant is usually very difficult for us to obtain. And the rigorous derivation is a little bit later, and it's done by Dive, Eads, and Krasovsky, and they derive this one rigorously, and we also get this constant term. The constant here is given in terms of this Riemann zeta function. Okay, so this is about the area kernel determinant or the Tracy rhythm distribution. And so for the determinantal point process, somehow we can also consider the so-called thinning. Thinning means that, okay, we have those kind of particles, and now we just take away one particle independently with the probability, say 1 minus gamma. When gamma is equal to 0, we just do not, when gamma is 1, we will go back to the original case. And now if gamma is between 0 to 1, we have a so-called thin process. And one good result is that if we have a determinantal point process after thin, we still get a determinantal. So we still have those kind of structure, and we can also have this kind of Fredholm determinant. And so later on, this idea is applied in the study of random matrix theory, and they just consider, so they consider the deformed area kernel determinants. They have the so-called deformed Tracy rhythm distribution, and now you see the expression is almost the same. We have the same function, we have the same structure. The only thing that this solution is changed. Well, we have the same we have the same homogeneous parameter 2 equation, but now we change this this boundary condition a little bit. We will get the Olver-Siegel solution. We can also see in Sheehan's talk, which is oscillating as x goes to minus infinity. And so we have this formula here, and now then it's also a very natural question to ask, so what's the logical asymptotics? What will happen when s goes to minus infinity? This is done by Bosner and Buckingham, and you see that, again, it is exponentially small. By the way, because of here we have taken a log, so this probability is exponentially small. But comparing with the previous case, this one goes to 0 much faster. We have s to the power 3 if gamma is equal to 1 for the non-deformed case. If we have deformed that, and with this power here, we go from 3 to 3/2, which is a significant change. And so if it goes to 0 much slower. And so here this nu is corresponding to this parameter gamma is equal to -1 minus log of 1 minus gamma, and this constant is also obtained, and which is given by the Barnes G function. I think the very interesting thing is that here the formula is obviously not uniform in gamma. You see, if we let gamma goes to 1, and here nu goes to infinity, so this formula here does not work. This is we can also see in Sheehan's talk, right? You see this kind of from a Hastings-McLeod solution to the Olver-Siegel solution, the transition is not trivial. If we study the parameter 2 solution inside, we may involve this theta functions. If we now study this kind of integral towards the Tracy rhythm distribution, and this is also a very challenging task. But recently, I think for the sign kernel, Bosner, Eads, and Dive, Krasovsky, they have made some very nice work in this area, and they have get a full picture for the sign kernel, how to see this transition when gamma is between smaller than 1 to larger than 1. But for the general, for the other kernel, I think this one is still a very challenging question to see how the transition go from this one, from this like the sub-exponential case to the exponential case. This order here is changed by, is deducted by half. Okay, so this is like we use the area kernel as an example to show you this corresponding to show you the corresponding problems, and for the other ones, and I think we can also have many results. And this is I think many people are interested in such kind of problems, so many people have worked on that. So if I miss any names, so please forgive me. And for the classical sign kernel, Bessel kernel, and we can study the corresponding Freud-Harmonic determinant, including the deformed cases. And here we also have the integral formulas, and and those kind of the integrals will involve the Panaway equations, and we can also get the large gap asymptotics. And we can also study some other Panaway kernels when we have some transitions. And in these cases, and we may have some different method to derive those kind of formulas, but one method is very useful is this Riemann-Hilbert method. And by the way, we want to mention here that for those kind of problems, if we use the Riemann-Hilbert problem to study that, we have 2x2 one, like in the Sheehan's or the Alfredo's talk, we have 2x2 matrix value Riemann-Hilbert problems. But now for our POC and hot edge POC kernel, we have a 3x3 one. So that's also the reason why we call them to be the higher dimensional kernels. And so this is our target, right? We want to study the similar thing. We want to study the Freud-Harmonic determinant for this kernel, for the POC kernel, and also for the hot edge POC kernel, and for both the gamma equal to 1 and for the undeformed case as well as for the deformed case. Okay, and here the interval is slightly different. This one is in the middle, so we go from -s to s. This one is near the hard edge, so we take it from 0 to s. And again, we want to know two things. The first one is about the integral formula. The second one is about what happens if the gap goes to, if the gap becomes large. And so to state our results and to state typically for the integral formula, we need to have this Hamiltonian. This is Hamiltonian corresponding to the POC kernel. And now you see the formula here will become a little complicated. For this case here, we have a Q and P. We have we have 8 functions. We have 8 functions, and but anyway, we can define this Hamiltonian, and this Hamiltonian will appear in the integral formula for the Freud-Harmonic determinant of the POC kernel. And in the area case, and we only have Hamiltonian depending on 2 functions, P and Q, so it's relatively easy for us to reduce one of them, so we get the formula obtained by Tracy and Whedon. And for our case, we don't know. It is too many things to do. We don't know which one to reduce. We just stay with our Hamiltonian. But I think that, and this Hamiltonian is convenient. I think in one of the Professor East's talk, he also mentioned that the tau function, or equivalently the Hamiltonian, will be actually more natural, appear in different kind of models in mathematical physics. And for our case, it's indeed, our formula is more convenient if we use the Hamiltonian. Okay, and by the way, the Hamiltonian is also equivalent to the one studied by Brinsky and Hakami and more than 20 years ago. Okay, and so this is our formula. So you can see now the formula becomes very neat if we use the Hamiltonian. So we just get this. This is a log of our Freud-Harmonic determinant. Now it's just given by this formula, and 2 times from 0 to s this Hamiltonian, and we can see. So now we have this integral formula, and we think that this one is in the sense of the Tracy-Whedon formula, because we have a closed form. And to make sure that this formula here is well defined, of course, we need to study the behavior as s goes to 0 to make sure that it is converging over there. And we also need to show that it's Hamiltonian is pole-free on the line, on the real line. So that's something we need to do. And after that, we can actually establish that, okay, this integral here is well defined. And moreover, we can also study its asymptotic as s goes to infinity. And from here, we can see now we have already seen this difference, right? When gamma is equal to 1 and gamma is smaller than 1, it's very different. And this is, again, the transition here is not uniform. This beta as gamma is, if gamma goes to 1, this beta will goes to infinity. Okay, for the Hamiltonian, the first one we have some, for gamma equal to 1, we have those, we only have those algebraic terms. And for gamma is smaller than 1, we have some kind of this oscillatory term, but now the amplitude will decrease. Okay, so this is our integral formula. And from here, actually, you can already guess. So what we will have for the large gap asymptotics, right? This is what we have. So here we just plug in. If we plug in this formula here inside, we can just get the asymptotics for the third hormone determinant. But be careful is that here, if we plug in, if we consider the large terms, there's no problem. We can get if we integrate, we can get the terms we have. But the constant cannot be obtained from this from the formula here. For the constant here, you need to just take all the contribution from 0. Later on, you are going to let s goes to infinity. You need to get all the contribution from 0 to infinity, which is a very challenging task. So from here, we can get the first of few terms, but not the constant terms. Okay, but not the constant term. And but with some other technique I'm going to show you later, and finally we can manage to get the constant. But not for the case of gamma equal to 1. For the gamma equal to 1, we know that we have a constant. We can derive, we can separate some terms depending on rho due to some kind of differential identity, but we still have an unknown constant c, and we have no idea what this number c look like. But when gamma is smaller than 1, and we go to the deformed case, first of all, maybe you see we have introduced one more parameter. You just make the problem to be more complicated. However, it turns out that this gamma parameter is nice. Right, we can also get this constant term precisely. Again, it is given in terms of the balance G function. Right? This is a very interesting thing to see here. So this is about for the PLC kernel. For the PLC kernel determinant, we can get these two things. Again, we see the similar pattern, and you can see for the leading order. For gamma equal to 1, for the undeformed case, we have s to the power 8/3. And when we have this gamma, and now this exponent again dropped by half. We have seen this kind of phenomenon in all the cases. We believe that this is maybe it's true for all such kind of problem, but we are not very sure what's the really reason behind that. Okay, so it's kind of this exponent, right? Exponent changing for this case. And so this is our large gap asymptotics, and then we can also say something about the applications. And actually, we are going to see that with the large gap asymptotic for the thin case, for deformed case, we can also say something about the original point process. This is something I think very interesting. And first of all, we have this original undeformed gamma equal to 1 case, and now after we get some information for gamma is smaller than 1 case, we can also go back to the undeformed case. And so, for example, here, if we let n to be this random variable, gives us a number inside this interval we want to study from mass s to s, and we know that for the exponential generating function, we have such kind of formula due to Sheehan-Likov. And now you think that if I choose gamma to be 1 minus this e to the power minus 2 pi mu, we just get the formula. We get our third hormone determinant at the very beginning, and it's this one. And so here, because our formula, our large gap asymptotic is actually uniformly valid for any gamma between 0 to 1. So for our case, if let nu goes to 0, if let nu goes to 0, gamma will goes to 0. So our asymptotic formula is still valid. And now we can expand the formula here on the left-hand side, and we can expand our formula here on the right-hand side here. Now we can have a matching. We can find the asymptotics for expectation as well as the variance for this number ns. So finally, it's possible for us to establish a central linear theorem and for this kind of quantity about the original point process when gamma is equal to 1. This is actually the asymptotic we get for the expectation value, and this is about the variance. And the other good thing is that recently, and in a paper by Sheehan and Claes, they have developed a method to see that if we have those kind of asymptotics for the deformed cases, actually you can establish this kind of so-called global rigidity bounds. This is, I think, the people in random matrix series, they always want to know this the fluctuation of the eigenvalues, and they want to establish the bounds. And for some general Wegener matrices, and the group like H.T. Yao and Erdős, they have established those kind of bounds. But now recently, and with the result by Sheehan and Claes, and for the determinantal point process or for the unitary matrices, it's possible for us to get a better bound, and this is the bound we have. It's based on our formula here, and Charlier derived this upper bound and for this global, for this eigenvalue fluctuation, and which is very good. However, of course, we can also expect that we have very similar lower bounds. Basically, you just change this small or equal sign to the large or equal sign. Maybe you need to you also need to change this plus sign to be minus sign. You can also expect we have the similar things. It actually means that, okay, although the position for the particles are random, but when n is not, they actually very close to the determinant. It's actually very close to the limit. And so here, we can also expect that we change the direction of the inequality. We can also get a bound, but the lower bound is very challenging. And recently, there's a breakthrough by Claes and Fass, Lambert, and Weber, and only for GUE, for this very simple toy model, they have established the global rigidity lower bound. But the task, but the method is not easy. They need to have this connection with Gaussian multiplicative chaos, and then you need to study the asymptotics of some Hankel determinants very carefully, and such that they can establish a lower bound. But once they have get the bound, their bound is, they say that they claim that the bound is optimal. It is better than the existing bounds in the literature. Okay, so this is one thing about the possible applications. And so this is about the POC kernel, and for the hard edge POC kernel, we can do something very similar, and we can also find the Hamiltonian. But now for this case, the function becomes we have more functions. Actually, here we have 12. We have 12 functions, and so we can. But anyway, we can find this Hamiltonian, and it says we can also find this kind of nice questions, and then we can establish an integral formula, which is given again. Once we have the Hamiltonian, the integral formula is very neat. We just go from in this small interval, we get our formula, and now we can also need to we also need to say this integral formula is well defined by starting its behavior as s goes to 0, and also we need to establish that its h tau is pole-free on the real axis. Okay, and this is asymptotics, and we have some very similar structure, I can say, but of course here the order will be a little bit different. We will have this additional parameter alpha. So finally, we can also get this asymptotics when gamma is equal to 1, as is done by my former student Yao and Zhang, and this is the case for gamma is smaller than 1. For gamma is smaller than 1, we can get the constant precisely. Again, gives in terms of the Barnes G function, the formula is true for any gamma between 0 to 1. It's uniformly valid near the point 0. So in this case, we can also get the similar applications like the central limit theorem and also the global upper bound. Okay, so this is about our results. Okay, so how many minutes do I still have? 10 minutes. Okay, so maybe I just give you some idea about the technical part. So here are some remarks for the proof. And so mainly we are using the Riemann-Heber method we have seen in Alfredo and Sheehan's talk. But for this case here, we will have a higher dimensional case, namely we have a 3 by 3 matrix valued Riemann-Heber problems. And they are integral in the sense of its asking and Kirby and Swanov is that they can give it in such kind of forms. And by the way, for this case here, this m can be any number is large or equal to 2. Can be actually, so this formula, the formulation is actually very general. You can get an arbitrary m dimensional problem. And so once we have the kernel in the setting, and then we can study, then we can have this classical formula, and we can study the logarithmic derivative of this Freedom determinant, and we can get such kind of formula because this k here is a trace class operator, of course, provided that this 1 minus k, the inverse exists. If this one exists, we have such kind of very nice formula. And now we can just associate this logarithmic derivative with the Riemann-Heber problems. And because this k here could be higher dimensional, so in general, this problem here is also higher dimensional. And then what's there? Then we have 2 problems, one for the kernel, and here, and then one is we have for the Freedom determinant. Now we need to combine them together. We combine them together. More importantly, we want to get a problem with constant jumps. So once we have a constant Johnson, we can do a lot of things. First of all, we can just try to derive the associated less pair. We can find the integrable system structure behind that, and then we can apply the Jimbo, Miwa, and the general theorem to get our Hamiltonian. Because you can see at the very beginning, the formula for our cases, the Hamiltonian is very complicated in terms of the function P and Q's. But in terms of the Riemann-Hill problem, it will be very nice. It's very simple. It's also very natural. So this is a very important thing. We can get the Hamiltonian structure. And moreover, and this one is especially important for us to derive the constants. And for the deformed cases, this is the observation by Itz and his collaborators that is tau functions. Or for our case, it's the Hamiltonian. It's actually equal to the classical action differential up to a total differential. This one is very good because with this kind of with such kind of property, we can have many useful differential identities. And now we can just transform the original differential identity about S, which is good but not very useful for us to get the constant. Now we can transform to the derivative with other parameters, and then we can just integrate with that parameter. Now it's possible for us to get the constant. So this is a very important observation for us to study the deformed case to get the constant. And later on, of course, we are going to use the Diphantzel steep-descent method to get the asymptotes. And for our case, we have high dimensional. So we may need to construct the G function defined on the Riemann surface because, we can also see in Alfredo's talk, sometimes you need to just choose a G function nicely such that you have the same large behavior, but you also capture some kind of local properties. And for our case, we need to do something similar, but now we need to go to the Riemann surface because, and now for our, we do have some entries. We do have some entries which is either above the main diagonal or below the main diagonal. So we need to be very careful such that this G function, the real part will satisfy our desired properties and the positive or negative in certain kind of regions. So this is something we need to do comparing with the lower comparing with the 2x2 or the lower dimensional cases. Okay, so I don't have too much time. Maybe I just show you here, right? This is the Riemann-Hill problem for the PLC kernel, and now you see some of them are very similar to the 2x2 cases. Like here is the lower diagonal, and right? Okay, but for our case, we have some entries and below the main diagonal and also above the main diagonal. So for that case, it will give us some difficulty when we normalize. If we normalize the logistic behavior, we may have some terms here, and now we need to ensure that when our parameter goes to infinity, it actually goes to 0. So that's the reason why sometimes we may need to have this function and define on the Riemann sphere. So this is one thing I want to tell you about the difference between the lower dimensional cases. The other one maybe I want to tell you is about here, this the tau function business I have mentioned. By the way, the first one is this differential identity. So the first formula comes from the paper by Dive, Itz, and Zhou about this classical differential, right? You differentiate the first, you consider the logarithmic differential of the first determinant. Now you get something corresponding to the resolvent. Finally, you can get entries in terms of our Riemann-Hill problem. And the next one is about from the Jimbo-Miwa theorem, we can get this Hamiltonian very naturally, right? You can see now the H function is given in terms of some entries in our problem. Now is very neat. It's very simple. And the last one is about here, the differential identity I want to show you is this one. It's something we mentioned that, okay, now you can just consider the tau function as a total differential as some kind of action derivatives. And now for our case here, we have some parameters. So you see like our parameter gamma. And now we can try to differentiate this parameter gamma here. First of all, so we can differentiate about the original variable S, of course. This is our general parameter. But now we have this additional deforming parameter, and now it's also possible for us to differentiate. And this kind of differentiation is very straightforward, actually. Once you have the formula for the Hamiltonian, you just do the direct differential, you can get this formula. Although it is very easy, but now it gives us a very nice identity in the sense that originally we want to study this kind of limits, this kind of integral here below. It is it can't give us the leading orders, but not the constant, because we need to have all the contribution from all the way from 0 to infinity. But now you see we can try to use the formula here to transform. We use the formula here to transform this kind of quantity here about the parameter beta. For our case, is actually gamma. And now from 0 to s, this is about the derivative for s, and now we have the derivative for beta. It's actually our gamma here. We just do a change of variable. And now the good thing is that we have the formula here because our asymptotics for all the functions are uniformly valid for all gamma is close to 0. We just plug in. And moreover, for the beta parameter, it's actually low. We know that when gamma is 0, we just get everything is nothing. When gamma is 0, we just take away all the particles. The probability must be 1. And then we have gamma, we integrate back, we can get this formula nicely. So this is the power of such kind of differentials. And so this is some technical part I want to show you. Maybe at the end, I will give you a summary about our work. Is that first we started the first determinant for the POC and the hard HPOC kernel, and we get the integral formula as well as the large gap asymptotics. And we see that this formula here, of course, is not uniformly valid. And when this gamma goes to 1, so the exponents will go from the super exponential to exponential. We go from 8/3 to 4/3, and this is for the POC case. For the hard HPOC case, is also similar. This kind of phenomenon also happens for all the other kernels we have seen so far. And then again, this one to start the transition will be very interesting, but of course it's very challenging. And the constant term here, we have obtained the case, we have obtained it precisely when gamma is smaller than 1, but for gamma is equal to 1, we still have something we don't know. We don't know this constant terms. Okay, and so I think I can stop here, and this is some references if you want to know more details about our computations. Okay, thank you very much.
Any questions? So you've got ARE, you've got PSC.
Yeah.
What about the swallowtail or the high catastrophes? Do they come in or not? Or?
As far as I know, we haven't seen those kind of kernels in the different models. Of course, we can ask that if we have different kernels, can we get similar problems? And I think that's possible, but of course we want to get some kind of motivation from different kind of models in mathematical physics.
Yeah. Okay.
Yeah. So for the
3 by 3 is third order expected to use 3 by 3 Riemann Hilbert problem, so if it's a fourth order or higher, it'd be like an n by m. Yeah. Okay. All right. Cool. Any other questions? No? Okay. So thank Dan Dai again. Thank you.
Okay. Thank you.
So coffee now till 11:20, and then back for Anna.
Okay, brilliant. Take your time. I need to cough. Sorry.
Okay, so welcome back to the last talk of this morning, and we're very pleased to have Anna Loureiro from Kent, who's going to speak on special function positive solutions of the DP1 hierarchy.
Thank you, everyone. It's a pleasure to be here and to be in such an expert audience. I'm not an expert on this, but I've been very much enjoying working on it. Anyway, first of all, thank you for all the organizers and all the nice time we all had here, including yesterday. Maybe far too long time, but doesn't matter. Okay, so let's, what am I going to talk about here? Okay, as some of you may know, I work in orthogonal polynomials, and of course I wouldn't go away without talking about orthogonal polynomials. So consider, but the topic here is orthogonal polynomials with respect to Freud's weight, or generalized Freud weight, or whatever we may want to call it. But essentially, we are considering a weight with a potential that is a polynomial, and then some algebraic perturbation. So essentially, that's what I'm going to talk about all this time. And but the main focus will be on these coefficients beta n that you can see here, that are the recurrence coefficients of this orthogonal polynomial sequence. So this orthogonal polynomial sequence, because of the choice of the weight, it turns out to be a symmetric polynomial sequence, and that's why the recurrence relation only involves these three terms. But coming back to what I wanted to talk about is, okay, we are going to consider these weights, and we are looking at these recurrence coefficients. And now you may wonder, okay, but all of this is known. And most of it is true. So the idea is to discuss how we can add something that is perhaps new, or I hope so. Okay, so again, let's go into the details. As I said, the aim is to describe those recurrence coefficients. And it turns out that those recurrence coefficients are very much linked to the discrete Panové-1 hierarchy. And so let's take it slowly and go for the orthogonality definition, just in case, just to make it precise. So so I'm talking about orthogonality on the real line. So the support of the weight of the measure is on the real line, or on an interval of it. But this time, we are really going to consider the whole real line. Anyway, so given any weight, we can always, by definition, the polynomials Pn's, so they always satisfy this three-term recurrence relation, although I don't like the name three-term because there's other polynomial sequences that are also satisfying a three-term but higher order. So it's a second-order recurrence relation. And as such, there exist coefficients alphas and betas, and of course it follows directly by definition on how we express them. Well, when the weight function or the measure is symmetric, then it turns out that these coefficients, they just go away. And that's the case what we are looking at, because we will focus on a case where our weight is a specific one, symmetric, and therefore we don't want the alphas. But anyway, there's always tricks, because we like symmetrizable things. There's always tricks to play around to go for the symmetric, from non-symmetric to symmetric, via quadratic decompositions or whatever. Anyway, but the betas are the ones we want to study. So of course we can compute them, we can do something, but as I said, the specification, is for a certain weight. And again, just going through a little bit on the background of orthogonal polynomial sequences, for a generic weight, I'm not specifying. Of course, these beta coefficients, because of the algebraic relation you have, or the recursive relation, those betas can be expressed as determinants, and actually as a ratio of determinants and the so-called Hankel determinants. For a matter of fact, given any sequence of moments of a measure, one will say that the polynomial sequence exists and is orthogonal to that measure, provided that these Hankel determinants here are actually non-zero. But of course, computing determinants is not something so nice. But we take advantage of that expression. But as I said, we are dealing with a symmetric case, which means that the moments of odd order will all be zero. So we'll have a bunch of zeros here. And for computational matters, it turns out that we have great advantage of just removing that zero component from the determinant. And anyway, and in such a case, of course, the even order and the odd order will go in parallel. They are related to each other somehow, but we can compute them separately. And that's what we do. We just compute. So this is just a matter of addressing computation, nothing else. So, and of course, just follows by linearity that your betas and your gammas, and the betas can be computed in this way. So I see in the audience some bored faces. Of course, for those who work on orthogonal polynomials, there's anyway, but be patient, bear with me, and we'll get there. Okay, so basically is what it can be used in terms of facilitating the computation or the numerics. And anyway, so coming back to the weight. But the weight, I said at the beginning, actually is a weight that can be written in this form. And it inherited, so it can be written in this something that is multiplied by this exponential with t to the x squared. And it comes directly from this type of weight. So remember, our weight is of that form, but the goal is with specific ones. So our weight is involving parameters like t and m, and it is of the form of exponential, x rho, and exponential of minus x to the 2m plus, bit of plus t x squared, okay? But it has that term. So it's even a simpler case of that. That's what, but no matter the weight, yeah.
Not a typo that is e to x squared.
Sorry? Yeah. It's the same. Because, no. Because this is, you're right, I should say m is bigger or equal than 2. okay? Now it's exponentially small. Yeah? But yeah. So, of course, I'm not having here details, but the omega naught, of course, needs to obey to certain conditions. So in particular, we want a Schwarz function or with rapid decaying at infinities. And anyway, but the ANs and BNs that I was mentioning before on these expressions, these determinants, they can be also expressed as other type of determinants, in this time as Wronskians of whose components are derivatives of the first moment. But one may panic here, but it turns out that for most of these weights, we can relate the following moments to the boiled down to the first ones. And there's ideas that we can use from the study of other cases where actually things become very simple. Anyway, so because of the expression of the weight, because of that exponential there, is growing, but doesn't matter. T can be real. And then we have automatically the Volterra lattice equation for the recurrence coefficients. And no matter whatever omega naught we consider at the beginning, we always have this. And we can compute things. So this is known as the discrete KdV equation, or the Kac-Van Merburg, or the Langmuir lattice. Yeah, so it's known in several ways, but I'll refer to it as the Volterra lattice equation. So we are going to take advantage of this. We are going to use this to study, as I said, not to any omega, but even for this specific case with that algebraic perturbation. I'll explain why the algebraic perturbation in a moment. So anyway, again, we're still revising, still going through, and it is well known that those determinants, those Hankel determinants, the capital delta n's, they can also be written as an integral, and actually it is the connection pretty much from there that follows the connection to random matrix theory, and because it is a partition function. Anyway, and it's also known as the Hein integral representation for the deltas. And, well, the polynomials, of course, by algebraically, we can also represent them as determinants. And it's kind of trivial. And often, it's even easier to not use the canonical basis here, but using a different basis to get advantage of the structure of the moments. However, we could use that technique to study such weights as we are doing there. However, it's not as evident that things would simplify greatly if we choose a different basis rather than this expansion into the monomials. Okay, so let's go a little bit of historical remarks for those of you who don't know. So there is a long relationship between semi-classical orthogonal polynomials and integrable equations. But perhaps the first one to come up with was Sheehan. Then there was a lot of works during the 90s, or late 80s and early 90s. But, and also in the 70s with Freud, but there were other semi-classical weights also considered. There were different approaches to the study, some more algebraic, some more analytical, but there was certainly ones that singled out to be studied later on, and that was the work, the proposal by Freud, and therefore the name Freud weights. And there was an enormous amount of contributions, but then somehow the theory went very steady. Nobody really paid attention till later when there was a connection to Painlevé equation thanks to Focus, Alexander, and Kitaev. And also a great paper to read is Alphonse Magnus' paper, where it really gives, well, it's a funny paper, as Alphonse, for those of you who know him, is a very special person. And anyway, so this paper by Magnus actually gives a big insight, and there's other contributions to that study. But essentially, as I was saying, if we have a weight of this form, so if you relate to this case, would be with m equal to 2. And in that situation, what we have is that our recurrence coefficients do satisfy this do satisfy this this equation, the discrete Painlevé-1 hierarchy, but with only with n. And there is, of course, a connection to the Painlevé-4 equation, and there's lots of studies around, and the connection to these weights has been well known since a while now. So this equation that we are seeing is indeed discrete Painlevé-1, and there's a huge, long classification on that. I'll come to that. So Nalini and Cresswell did a lot of work on that, but I will get back there. Anyway, where was I? Okay, so let's go to this weight finally. So we can see the previous examples with m equal to 2, m equal to 3. There's a lot of information there, but we don't need to restrict ourselves to 2, 3. We can continue. So it turns out if you continue, the first thing to do is to compute the moments. And the moments, they are by definition given by this expression. And if you compute the moments, well, it's kind of simple to get to these relations. I'm afraid that none of us know how to simplify this expression further. Perhaps Adri will find a way, but so far I don't know. But we are happy with this expression. We like hypergeometric functions. So any linear combination is fine with us. So most importantly is that, well, of course, the odds or the moments, they will vanish. They are all 0. And then regarding the even order moments, what happens is that, well, they will be the kth order derivatives of the original, the first moment. And as I said, if we go back to the beginning, we can look at as Wronskians of successive derivatives of the first moment. And again, that's all we need, actually. And we don't need to do differentiations, because nobody wants to do differentiations. All we need is to do shifts on the parameter. So this can hint why this is useful to have, but actually, this algebraic perturbation also helps in other regards that I will talk in a moment. But in any case, the moments that have this linear combination of hypergeometric functions, I shall say here we have a 2fm function, but in reality it's a 1fm minus 1, because there's always, depending on the choice of the k, one of the parameters cancels out. Okay, but still having a 1f3 or 5, it doesn't, yeah. The generating function, yeah, I mean, the best one is pretty much similar to the integral. It's just the Laplace transform of that, yeah. Yeah. So that's, I think perhaps the integral is much easier. Or the differential equation is quite simple. Yeah, a differential equation in T. Don't know. Don't think so. No, no, definitely, no. But I didn't, yeah. Yeah. Sorry?
Like a factorial very much on top and a factorial in the denominator in your sum? Do you have to restrict the t a little
No,
bit?
no, 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 they converge.
Okay.
Yeah, they converge. Remember K, sorry. Yeah. Yeah, I'm not in divergent, sorry. Okay? Yeah, but the moments, sorry, the moments do satisfy this differential equation. It's a rather simple one. It's just a representation. But it is what it is. But hypergeometric is fine. I like them, so it's okay. So in terms of going back, so the moments, as I said, are represented via that hypergeometric function or linear combination. We don't really care much about how complicated or simple it is. But anyway, but the polynomial sequence satisfying then the recurrence coefficients, as I said, mentioned, and I repeat it here, they can actually be written as the log derivatives of certain quantities that happens to be the Wronskians. And the moments, as I said, so if we go back before, actually I put here the expression for the moments, but actually what is more interesting is precisely this relation here, which then corresponds to a shift on the parameter. So the moments, then we can compute the betas or the recurrence coefficients in this fashion. And okay, so that's despite we have this expression for the moments, we are going to the idea is effectively these betas, they do satisfy a discrete Panové equation, and we are focusing on the case where we have these initial conditions. And it turns out that we do know that the solution is always positive, and that's the solution we're looking, because we are sitting these betas in the context of orthogonal polynomials with respect to a positive weight on the real line. So definitely those coefficients are always positive. They do exist, and then we just want to study further. So anyway, it turns out there's plenty of ways of deducing the equation for those recurrence coefficients. So one way has been done by some people, Banassi and Moro, and also Bonora Martellini earlier on. They developed in the integrable systems language a way of getting the expression for those coefficients. So basically, what we are seeing here is nothing but the Jacobi operator associated with the three-term recurrence relation of not the monic polynomials, but the orthonormal. So anyway, but it is well known that if you have a Jacobi matrix is always symmetrizable, that means that you pass from to deal with the orthonormal polynomials. So then, of course, you can iterate. So essentially, what you can see is that these beta n's can be computed using basically the nth coefficient on the expansion of x to the 2m. Anyway, I won't enter to the technicality, pardon. So let's go back. And so basically, they can be seen. So what is this v to the 2m over there is nothing but you pick up this matrix. You can see that the 2m minus 1th power of it, and then you look at the n, at the row n, column n plus 1 entry, and what you get is essentially an expression that would give you for these vn's. Now, all the rest comes down as the compatibility conditions that arise on the fact that we are dealing with a weight of this format and the orthogonal polynomials associated to that. That's one way. There's many ways of expressing it. And then in particular, if you take m equal to 2, m equal to 3, and so on, what you find, so as you can see, what is arising there is nothing but the first bit of the dp1. And then here, it's not really, doesn't look like the dp1, but it's the dp12. I don't know how to call it, but I'll come to the notation in a moment. And all the rest, as I said, comes from the compatibility condition. But as I said at the beginning, I'm an orthogonal polynomial person. So I like to do it from the orthogonal polynomial way. So what I'm going to tell you soon is exactly what I've just said, but in a different language, if I may. So it turns out, okay, actually, no, I still have this slide to explain. Yes. So it turns out, well, as I said earlier on, Nalini, Joshi, and Cresswell, they teach a lot of classification or explanation on this front, on the hierarchy of the dp1. And also the connections to the continuum limits of the differential equations. Okay, so effectively, you either using this method or the one that comes next, we deduce exactly the same equations. So this one is a special case of the dp12. Oh, actually, I wrote it here. Yeah, dp1 up 2 hierarchy, and so the goal for us. Let me take. Oh, sorry. What am I doing? It's going back and forth. The goal for us is to study this kind of recurrence relations, okay, or to have a look again, or revisit these recurrence relations. Okay, as I said, I'm an orthogonal polynomial person, so I like to deduce from to explain from what happens in the recurrence on the orthogonal polynomial viewpoint. So it turns out that our weight function, being this one, satisfies this differential equation. And this is the Pearson equation, which appears, it's inherent in condition to the semi-classical polynomials. And so either they are the discrete semi-classical or the Q semi-classical. It's always the Q Pearson equation, the discrete Pearson equation, whatever. But it's always a first order, ODE, with polynomial coefficients where the degrees of this one -1 and this one -2 is always bigger than 0. Anyway, so from this differential relation, it comes straightforwardly by integration by parts that you can express in this case, because of this x, you put the x there and you do the differentiation, and you can actually you look at the expansion of these polynomials, the derivatives, and in the sequence Pn. So basically, the coefficient to the highest power will give us the expression for the two highest powers will give us the expression for the equation that the recurrence coefficients satisfy. And it goes very simple. So you pick up this, you write like, we always can write it like this. The orthogonality means that you only involve 2 m terms up, 2 m terms down. Now you do integration by parts, and in a way, just using the orthogonality weight and playing around. And it turns out that those rules will actually satisfy these equations. But on the other hand, I can easily bring this equation into the 3-term, or this relation, or differentiate the 3-term recurrence relation, and then substitute, and compare, because it compare the coefficients in Pn, Pn plus 1, and so on, so forth. And then you will have alternative expressions for this, and that's where it comes out straightforwardly from the Volterra equation, what happens there. So you get actually the two equations repeated because there's a symmetry between those that are above the n plus k, or 2k, and the n minus 2k coefficient. So then we clean it up, and actually what we get in the end is precisely, the equations right here. So either way, pick the method you like the most, but those are the equations we get, and we can continue on and on to m equal to 3, 4, whatever we like. So let's go to the weights. As I said before, lots has been done and lots of contributions, and I do not claim here to revisit all the massive contributions that came to the studies of the asymptotics of these recurrence coefficients in several aspects. So I'm just quoting a few, nothing but that. So there's a lot of analysis on the asymptotic behavior of the recurrence coefficients of any, actually, you can consider minus x to the 2m and then any polynomial next to it. So here, well, we just take the tx squared, but actually you can have a tail of a certain polynomial, provided that that polynomial does satisfy a certain type of conditions. Or you can even add logarithmic terms. That's what is happening, again, provided that it satisfies certain conditions. And you can read, yeah?
So no condition on C?
Oh, T can be real. Doesn't affect.
No, but it's strangely. Okay. I will ask later.
Yeah, I mean, you can even have Q, any polynomial there of degree lower than 2m. Am I late? Oh, okay. No, not yet. No, I'm not doing. The varying weight is used to deduce this. Okay? Yeah, definitely. If there was the varying weight, I would not say. Yeah, it's okay. It's okay. So effectively, you can consider other polynomials or logarithmic terms, provided that we have functions that are of a certain variation or bounded variation condition that they need to obey to. Yeah? So in any case, the coefficients, they do behave as algebraic, as n goes to infinity. For large n, they do behave as n to the 1m, and with some coefficient in front. Anyway, in terms of the zero distribution, this is also known, and here I'm adding the reference to Kellers and Van Asse, but actually their paper, and there's other papers on this, but they refer to this varying, so the zero distribution of the ratio asymptotics first to varying weights, which means that your recurrence coefficients actually grow with n. But there's other references. So in their paper is a bit more general than to this one. So actually this is not really what you will see in a paper, but we use the results there for their type of weights. Okay, it follows there's several contributions as well on this. Again, I don't claim here to quote every one, but what has been used was their results on the asymptotics. And it turns out that the zeros of, so here we are taking this, it's a rescaling, which is a typical thing to do when you're dealing with polynomials on unbounded supports. Then we do this rescaling, and that's what, there's a second index over there that is being used. But the zero distribution follows this hypergeometric, or the Gauss function, if you like. And okay, so coming back to the quadratic Voigt weight, and so in this case, we're taking m equal to 2, just because it's simple. But then we will take it for m equal to 3, and I'll explain why we are doing this. So it is well known, and Nalini's talk at the beginning, Nalini gave a great introduction. And if you take the betas, you assume they behave all the same, call it beta, then you can look at the behavior of this function. Well, I put beta plus beta plus beta, which is 3 beta, yeah? But we all know how to solve this, and this gives immediately how the coefficients, so it kind of gives a formal asymptotic approach to how the coefficients behave for large n. And effectively, they will go around. But if we fill around the curve that comes from here, it's straightforward. It's an algebraic curve. We can solve it. And but it's but perhaps, sorry. Oh no, I'm sorry. It's coming. Need to be patient, isn't it? Okay, but when we look at this, there's clearly a flavor of even and odd terms. And if you do any computations, you feel that there will be a different behavior for the even ones, the odd ones, and that's. I shall say one thing here. This rho was the 2 lambda plus 1 before, but rho, I'll explain why rho is easier. So instead of looking at thinking of all the betas behaving the same, let's do this. So think about all the beta 2n's, the even order, to behave as a function of n. Let's call it u. Okay? And think of all the odd order to behave as a function of n. Let's call it v. So instead of looking at, as before, all the v's, all the betas to behave like a function of n, now we consider the even order to behave as a function, and another one. And then we have this coupled system of the two functions. But again, we are dealing with something that is quadratic, and we can solve it. Of course we can. And of course, they are related to each other in various ways, pardon me. And then we perhaps, and if we solve it, so here what are we looking at? So the u function, when rho is equal to 0, actually is even easier. So the v function is this one, is this blue arc, and then continues with this pale pink arc. So this curve that you're seeing here is exactly the beta curve that appeared before, the 4 beta times 3 beta minus t over 2n equal to n, okay? So that was the curve coming up here. And, oh, I forgot the term. I'm sorry. There's plus rho times, well, anyway. So when n is odd, then there will be a rho here. Anyway, but the curves, the u curve, when rho is equal to, oh yeah, I said rho equal to 0. Okay, sorry. Gosh, my mind. Anyway, so when the v curve, the capital V curve, will be this one that goes like this. Pardon, the capital V curve will be this one that goes like this, whereas the capital U curve will be this one. And there's a curve over there, of course. So if we compare with the little un's, so what we are doing here, oh, I should have added there. What are the dots that we are looking at? It's the beta, so the red dots will be the beta 2n's, and beta 2n minus 1, and wait, yeah, that's right, yeah, oh, where's it? Okay, the beta 2n minus 1, so the odd one, odd order ones, are these dots that being plotted, and it's effectively the curve. So if you look how they sit well, for large n, we did know that, right? It's no surprise. What it is surprise is that they are kind of sitting on the two curves. And there's a region here, there's a gap region where there's a bit of detaching from the curve. We can identify actually what is this interval that is a bit not so nice. Okay? Well, this is for rho equal to 0. But if rho is different than 0, then, well, we no longer will have this cusp over here, and everything smooths out. So one may say, well, with rho is a little bit more complicated, but actually there's a lot of advantage of using non-zero rho. And in terms of the behavior of those functions, there's lots of things that one can deduce directly from these equations, and they are kind of useful to understand on the actual little UNs or the beta even order and beta odd order. It turns out, well, that the U functions are bounded above by the curve when you have non-zero rho. So when you have non-zero rho, the U, so the even order ones are bounded above by the curve when it is rho equal to 0. And the V's is the other way round. So they are bounded below by the curve when rho is equal to 0. So it turns out that when rho is equal to 0 is separating the two of them. And this gives us a bounds. How about for negative rho? Now, negative rho, we need to be very careful. And I'll give a few more comments when rho is negative. But for the purpose of the curves U and V, capital U and capital V, for the purpose of the curves, there's this immediate relationship between them when we go for rho negative. But there's a caveat when we go to rho negative. I'll come to that because that weight will no longer converge. Okay, so that won't be the weight. But I'll come back to that, why we look at this. So essentially, we can see that all these curves, they sit like this. They are very, there's obviously, there's all sorts of monotonicity behavior and the minimums, and we can identify all this. This follows kind of straightforwardly from the coupled equation, but I'm talking about the curves where the dots will sit. Okay, so as I said, from the algebraic curves now with rho positive, oh, I forgot, there's plus. Can you see here? Plus rho. Okay? I did plus rho. Anyway, so when we compare, so we have these curves, and now the idea is to compare to the system. So now the little u's are the even order betas, the little v's are the odd order betas. So this is the discrete system, or the coupled discrete system. And here is the capital U as a function, continuous function of n. So what we are seeing here, well, is essentially the solutions of this system of algebraic equations, but it turns out we are looking for the solution where V is above U for other perspectives, which means this will be our V curve. We don't want this one, we don't want this one, and this will be our U curve. And now we should compare when we put the dots on top of it. And this is what happens. They really go very close. So in this case, we are taking rho equal to 2. And if we take rho equal to 5, it goes much closer. If we go back to the case where rho was 0, was actually, there was this gap. And I'm not claiming here there's no gap, because there is. As it is plotted in this instance, we can barely distinguish. But if we zoom in, then we will see there's a bit of separation between the dots and the curve, but not that big one. So for the sextic case, we have this dp1, 2. Am I okay with time? 5 minutes? 6? So anyway, so the m equal to 3 case, then you have this dp1, and then we do the same procedure, nothing new. But this time we are dealing with a cubic instead of a quadratic. It's okay, we still can handle this. And well, we just do some changes of variable, and now you can see that we can actually easily hold and study the curves in the new variables. I'm not going to enter into the detail, but in fact, what happens is very much similar. So this, what we are seeing is the sexy case, so m equal to 3 here, and with rho equal to 0. So there's this bit of detachment. When m is equal to 3 and rho is bigger than 0, this is what happens, okay? And you see, if we zoom here, there will be up, above, and up below. There's no such thing as. In fact, oh yeah, I had so rho equal to 2. And if we do the difference between the dots and the curve, what you see is this gap. Of course, in this region here is the critical region, and we can identify it. It's precisely there's a gap that depends on t and on the choice of the t and the rho, of course. And there's an interval here where the dots are a bit distant. But I'm not sure if you can see, this is 10 to the minus 2, okay? It's the biggest.
Do you do it in the other equation when rho equal to 0 as well?
Yeah.
So it's important that it is so large?
Oh, we tried. Okay, if you put t smaller, it's when it is large, the t large, it's when you can see a bigger gap. Where if t is, isn't it? If t is smaller, you don't see that big gap. So that's why I put the t20 to show a big gap. Yeah. So and as rho is bigger, actually it smooths a bit more. But that's not so surprising, because if we look at this, at what happens when rho goes to infinity, then it blends in with the n. Anyway, and here, if you see, it's 3 to the 10 to the minus 3. Okay, and here is 10 to the minus, I can't even see it. 10 to the 5 to the 10 to the minus 4. Okay, so that's what happens with m equal to 3. Then we can continue. So and what about if rho is negative? So we need to be careful. Of course, we can only go up to -½ on that weight, because otherwise that is not the weight of any orthogonal polynomial system. However, the recurrence coefficients are defined per se. So there is an orthogonal polynomial sequence with those recurrence coefficients, even if you consider rho to be -5. But it means that this weight is not the orthogonality weight, okay? But the recurrence coefficients, they do exist. There's no reason not to consider them, but we might not consider them because a simple reason. So look what happens. So this is with rho equal to -½ -1/4. So what happens is that the curve, so instead of following, remember that the little u's were following, so here when you change the rho, it flips. The u's become the v's become the u's in terms of relation to each other. And what happens is that now they are no longer following the blue curve that you're seeing here, but they are following this curve before. So the other solution, is also a solution to the coupled system of algebraic equations. So they are following this curve, and then they catch up to follow the other curve. So they jump from one side to the other. And the blue dots go like this. Okay? So the larger or the more negative the raw is, the more smooth this becomes. But the weight function is no longer that, I repeat. What about if you add this? But I think I'm exceeding time. I'm exceeding, yeah. So, yeah, you may wonder, well, are we adding just terms? Are we just playing around? Why are we putting this tau x to the 4? And actually, this brings a lot of fun to the picture. A bit more evolved, the analysis, and I'm very happy to have Marta here because actually in her work and her thesis was a source of ideas and things. Anyway, so the moments, okay, they are not good, but again, hypergeometric, who cares if it's a bit more hypergeometric, doesn't matter. The weights still satisfy a differential equation, slightly more complicated, but nothing special. It's all linear, it's hypergeometric functions, right? So then the recurrence coefficients, they do satisfy, well, there's a bit of more perturbation, but as you can see, there's a kind of a perturbation inherited from other things. And there's a differential equation for the recurrence coefficients. And now, there was these early works where the people were looking at this potential and into different, so in some emission random matrices or models. Anyway, where people look at the beginning and at the late, and it was actually assumed or proposed it could be chaotic behavior in this critical region here. It is no chaotic at all because there's an order. Effectively, so I go to Marta, who is in the audience, and they looked at this kind of weights. There's no algebraic perturbation there, but effectively, the algebraic perturbation can actually help and smooth things out. Anyway, and it is they studied this, and what happened? They look at the curve that gathers all the data that comes from the recurrence coefficients. And as I said, there's no chaos over there because actually there's a lot of order. So these are the order 3n, 3n plus 1, and 3n plus 2 points. And there is clearly a curve connecting. Yes, I'm completely exceeding time. People want to have lunch. And so I skip, and I think. Thank you.
Any quick questions? Quite a few. Hang on. Let's go to Alexander first.
To the very last part on when you have capital N. When you have capital N, when you introduce this sort of, So usually people consider this now as a varying weight, and you have both little n and capital N goes to infinity and keep some ratio. And there are very different regimes comparing to. But here you just still consider only n, little n goes to infinity.
So here, this is not our work, it's the work of Marta and Antonio Moro and doing. And they were considering this as a scaling and looking at the recurrence coefficients.
No, so the capital N fixed, and
you consider
large n.
Yes, yes. So it's not the two regimes, it's not the varying weights, yes, as we normally do for the asymptotic,
So, what is the actual asymptotic behavior then of the beta-ns? Do you have formulas?
Sorry?
Do you have formulas for the asymptotic behavior?
Yeah.
Okay, but
Oh,
you didn't show them.
Sorry?
You didn't show them, right?
No, I didn't show explicit, but there's, well, in a way, I showed the leading term, but we have several terms down. Yeah,
Okay.
but there is one, yeah, formal and not so formal, and there's more. Yeah, that is known.
Could you go back to 18 or thereabouts, where you had the one curve and the two curves? Yeah, that one will. Yeah, perfect. Further on. Next, sorry, I miscounted. One of the plots where it goes from the period 2 to the period 1.
Oh, sorry, after.
Up.
Yeah. Yeah.
Yeah, that one.
Yeah.
So if you were, so that looks like from a dynamical systems perspective, you're looking at a period doubling bifurcation. And what would be really interesting, so you're starting from the left and going to the right, and that detaching is exactly what you expect to see. If you started from the right and went to the left, you'd see a really nice delayed bifurcation, a canard. So it would actually stick to the period 1 curve for an order kind of
This
logarithmic, looks like order 1 distance,
Yeah.
before rapidly jumping to the period 2, which would be kind of nice to see.
Yeah. And yeah, that definitely, and especially when it goes for the negative and to the transition, because they capture, they bounce. But I'm afraid my knowledge of dynamical system is not. Maybe, I don't know.
Yes, why we still have this picture? It is I'm kind of very intrigued, because when we, in our old paper with Blecher, consider it, well, varying weight, when we had on the right-hand side little n divided by capital N, we have almost identical picture, but of course dependence on the limiting Rn on this ratio, on gamma. So everything that was to the left was 2 interval, and it was indeed jumping. And then we have 1 interval when it is greater than lambda critical. And in transition is given by Pinlever 2. So, but it is, yes, it is a picture exactly the same.
I think it might
Yeah,
be
but
related.
it is
yeah,
different
yeah.
different functions. So here you have dependence on little n, we have dependence on gamma. There is a finite number of pictures. Yes.
But you see the picture for m equal to 3, if I plot it here, you don't notice the difference. Oh, yeah. Well, of course, there's difference in magnitude, but we don't really notice the difference, yes.
Okay, so thank you. Let's thank Anna again.
Oh, thank you. Thank you.
And back at 2 for the last talks of the day.
Oh, nice. There's 2.
Chris and I had Dinesh have a paper on exactly that phenomenon in the other direction.
Grab this.
Oh, yeah?
from you.
Oh, yes, sorry, otherwise I will go lunch.